In 7.3, we're going to again be looking at volume, but from a different point of view. Again, I'm going to use this picture up here to kind of remind you of in 7.2 we were looking at volume, but the way we made the three-dimensional shape was the technique called solid of revolution. We took a shape and rotated it around a line, and it made a three-dimensional shape. In this section, it's going to be a little bit different, and the best way I can kind of get you to see the idea here is with a few animations here in the next slide. Okay, so if you kind of look at these animations as they go throughout this slide, what's happening here in this section is the little areas that we have, or that we were using maybe in 7.2 or even in 7.1, the area defined by some functions, we're not going to rotate that over an axis anymore. What we're going to do is we're going to let that area be the base of a solid. And sticking out of that base will be certain shapes. So if you want to look at this top left corner example, the bottom of this solid is the shape given by the square root of x function from 0 to 9. And what's happening is we're putting these semicircles in there, and that's what's defining our three-dimensional shape. So these shapes that we're going to be looking at here will all have a flat bottom. The other side of these three-dimensional shapes will have varying different looks to them. In this second, or this top right example, we have equilateral triangles sticking out of the base of this solid. Isosceles right triangles, we have squares in this bottom right corner example. Ultimately, what's happening here with these problems is, again, these areas that we have in our xy plane that we've been seeing since 7.1 and 7.2 are going to serve as the base of a three-dimensional solid where there's a certain shape sticking out of that solid. And of course, you can see in these animations, I don't know exactly how many of these what I'll call slices there are, but certainly if we want to find the exact volume, of course we're going to need to put an infinite amount of slices there. We're not going to worry about approximating because of course we know how to find an exact volume, and it's by integrating or adding up an infinite amount of these particular slices, whether they're semicircles, triangles, squares, or what have you. Okay, so let's start talking about how we can approach this topic. So just imagine slicing some cheese to find its volume. If you were to do that, of course we could slice the cheese into as many slices as we wanted to, but I'm going to slice it here into these 5 slices. We of course know that each of these slices has a height, a width, and a length. And I guess the main reason I need to point out those dimensions is because it's just a rectangular slice. These slices are called cross sections. That's why this topic here is volume, but we're finding volume because of these known cross sections. So in this particular case, we have rectangular cross sections, and of course we could find the volume of each of those cross sections. The volume of a rectangular prism is just the length times the width times the height. And of course we could do that for every one of these slices. This is just another rectangular cross-sectional slice, but I think the key here to realize is that it's different dimensions, but it is the same shape. And if you think back to that animation, the animations you saw in the last slide, if they were semicircles, they were always semicircles. If they were squares, they were always squares. So that's the key. These cross-sectional slices are never going to change on you. So if it's a rectangle, it'll always be a rectangle. But ultimately, to find the volume of an object by slicing it, we just need to add up the volume of each of the slices. So how do we extend this to shapes that are more complicated, of course? Well, here we go. We have this particular, I guess, bean kind of shape, so to speak, that goes from A to B. We know that somewhere in here we have a cross-sectional slice. Of course, I'm drawing one in here to kind of illustrate the concept, but of course we want to imagine that there's an infinite amount of these slices that we're adding up the volumes of. And of course that would give us the exact volume of the overall three-dimensional shape. So of course this bean shape has some sort of area. We don't know because there's no equation for it, but we can say that it's an area in terms of x. And of course, the width of this slice, I'm going to call delta x, or of course, as you remember from 7.2, that's just a dx. So there's two ways to slice shapes that we're going to have to deal with. When we have vertical cross sections, that means we're slicing perpendicular to the x-axis, or it could be worded as being sliced parallel to the y-axis. Ultimately, to find the volume of this three-dimensional shape, all we need to do is integrate the area with respect to x. So the way you should be viewing this is that is the area of the base. As we remember from 7.2, volume is just big B, which is the area of the base, times the height. Well, we really didn't call it height in 7.2 because we flipped our discs on their side, so we call it a width. But that, I guess, in this case, would be the dx, or the width. So ultimately, I actually hope you're seeing this as the same formula that we used in 7.2. It's just in 7.2, we knew that we were dealing with disks, so we could be specific. We knew the area of the disk was, of course, pi r squared dx. So if we had a disk, the volume was pi r squared dx. If we just have some random shape because we don't know what it's going to be, then we can just generalize that to say that it's the area of the base dx, which is again the same exact thing we did when we were dealing with disks. So I think that's a very important thing to point out. If you're seeing this as some different approach or different concept, I think you might lose the fact that 7.2 and 7.3 fundamentally in terms of this formula that we're using is the same thing. Of course, we can slice in a different manner. If we have horizontal cross sections, that means we're slicing perpendicular to the y-axis, or of course another way to say that is parallel to the x-axis. Once you realize that, just like you saw in 7.2, nothing really changes when you do things horizontally, other than the fact that everything needs to be in terms of y instead. I guess bottom line is this, other than all of this stuff right here, which I think is very important that you see in terms of connecting 7.2 and 7.3 with regarding their concept, I think really the bottom line you should take away from all of this is this one fact. Integrating area equals volume. No matter how these examples kind of proceed that we're going to see in these next few slides, the bottom line is if I tell you an area for a particular three-dimensional shape, all you need to do is integrate it. Every once in a while you might run across a problem where it simply just gives you the area, and you need to know this one fact here so that you can see it as an easy problem. Integrating area equals volume. Okay, so let's take a look at an example. Here we're going to look at a square cross section. So the slices we're going to be seeing here will be squares. The first thing we have to start off with is our area that we're going to use to have squares sticking out of it. Again, remember these areas, or these volumes, I'm sorry, of these three-dimensional shapes have a flat bottom. And sticking out of those flat bottoms will be different shapes depending on the problem we're looking at. So we've seen this before. We have two functions where they don't tell us anything about the bounds, so we have to set these two functions equal to each other and figure out where they cross. So once we figure that out and graph it, remember back from 7.1 and certainly in 7.2, drawing a good-looking graph here is going to be key to kind of setting these problems up. So we have our area here, so I'm going to go ahead and shape that in. This yellow part, again, is going to serve as the bottom as a base of a three-dimensional shape. And sticking out of the base are going to be, in this case, squares. So that's going to be the base of our solid. So it's kind of hard to draw in a flat 2D space, but just imagine squares sticking out of this yellow base here. Of course, ones right here are going to be a little bigger, The ones closer to the tinier spaces in this particular area will be a little bit smaller. But ultimately, going from left to right, we have a bunch of squares here making up that solid. If you need a kind of perspective shot to maybe appreciate what this might look like a little bit more, if you imagine these squares, again, the ones in the bigger part of the area will of course be bigger than the ones in the smaller part of the area. Ultimately, we're going to get some sort of shape that looks like this. I believe these are much more difficult to kind of visualize than the ones in 7.2. 7.2 probably wasn't too bad, but these can be a little more difficult to visualize. And luckily, like 7.2, your ability to visualize these in just a very basic way is really all you need to help you attempt these problems. Okay, one thing I kind of neglected to say earlier is the reason I know these squares go in vertically like this is they're telling us that we're finding the volume of a solid if the cross sections are parallel to the y-axis. And of course, parallel to the y-axis is another way of saying vertical. And of course, we already know that we're dealing with squares here. Okay, so let's start with what we know. We know the volume of these solids is the area, and we're integrating with respect to x here because we're doing this with vertical cross sections. So how do we find the area of one of these squares? Because once we do, that's what we're going to integrate. Once we find what the area is of one of these squares, that's all we're going to do is integrate that. So I'm going to go ahead and draw in my representative rectangle, just as you've seen in 7.1. Kind of drawing that in will help us figure out what we need to figure out. So what I'm going to do here is take one of these squares that's sticking out of this solid and kind of tear it off the 3D shape and lay it flat right here, so we can kind of see what we really should be focusing on. If I take one of these squares and rip it out of the solid, so to speak, and lay it flat, you can see here that the height of the representative rectangle corresponds to the side length of our square. And again, remember what the goal is. We need to figure out what the area of one of these squares is, because once we do that, we're going to add up an infinite amount of those volumes, or areas I should say. And of course, that's done with integration. So how are we going to find the area of the square? Well, we of course know that the area of a square is just side squared. But again, the side of these squares is corresponding to the height of one of these representative rectangles. So how do we find the height of the representative rectangle? Well, anytime it's a vertical rectangle, just like you've seen in 7.1, we'll just do the top minus the bottom. The top of what the rectangle is touching minus the bottom of what the rectangle is touching. The top of the rectangle is touching the x plus 2 function, and the bottom of the rectangle is touching the x squared function. Of course, we need to take all of that and square it, because to find the area of a square, it's side squared. So again, keep in mind, the side length of these squares corresponds to this function. And of course, we need to square that because we're trying to find the area. Just like you saw in 7.2, the setup is really everything concerning these problems, because that's pretty much it. Once you set this up, it's a fairly easy integral for the most part in these problems. So to kind of just quickly go over those steps, because I think the setup really deserves the most attention here. When you square out this, it kind of turns out to be a long mess because there's really no like terms that combine. But luckily, even though it's a mess of stuff here, all we need to do is integrate each of these terms individually because they're separated by pluses or minuses. So when you do that, plug in the top bound, you get 64 tenths. Plug in the bottom bound of -1, you'll get -17 tenths. And of course, when you add those two, you'll get 81 over 10 as the volume of this solid. Okay, again, we have another example of known cross-sections kind of problem. Again, the key to these problems, I think, is getting a good-looking picture to see what's going on here. Our function 1 minus x over 2 is the top function. Our bottom function here is -1 plus x over 2, and you can see right away that we're slicing perpendicular to the x-axis, and because of that, that means we're going to have vertical slices. And these slices are going to be made out of equilateral triangles. So to give you another perspective shot kind of what this looks like, imagine we kind of take this perspective shot and you can kind of see what's going on here. We have really big equilateral triangles here at the left side, which would be right here, because that space right there would produce pretty big triangles. Of course, the triangles here closer to the tinier part of this area, which would maybe be right here, aren't going to be as tall. So what's dictating the size of these equilateral triangles is, of course, the area that we're dealing with, since we have equilateral triangles sticking out of the base of what we have here shaded in blue. Once we realize that, it's just a matter of finding the area of one of these equilateral triangles and then, of course, integrating that. So this is probably a formula that not many of you recall, if at all, but certainly one you're going to need to commit to memory. To find the area of an equilateral triangle, assuming you know a side length, is this formula here. It's the square root of 3 over 4 times the side squared. So just like you saw in that last example, I'm going to take one of the equilateral triangles that's sticking out of this base here, shaded in blue. I'm going to rip it out of that solid and lay it flat here, just so we can kind of see it a little bit easier. So of course we know an equilateral triangle has all equal sides, and the side of these equilateral triangles, and this is the key, is corresponding to the length of our representative rectangle. Once we realize that, we just need to find the length of that representative rectangle so that we can figure out how long the side of each of these equilateral triangles is. So to do that, just like you saw on the last slide, because we're dealing with a vertical rectangle, we just need to take the top of whatever it's touching and subtract away the bottom of whatever the representative rectangle is touching. In this case, the top of the rectangle is touching our top function f, and the bottom of the representative rectangle is touching the bottom function, which is g. This actually simplifies quite nicely, even though it looks like a mess. We have a 1 and then a negative that needs to be distributed here, so that becomes plus 1, so that's a 2. Here we have a negative x over 2 minus an x over 2, which would just be a negative x. Don't forget, all of that needs to be squared, and that's the area of these triangles. The area of each of the triangles that we're dealing with here is given by this function. Once we know the area of these rectangles, think back to the first slide here, we know that we need to integrate that area, and we'll find the exact volume of this solid. So again, hopefully it's not too bad when you're doing these problems. A lot of the times it's fairly basic integrals you're dealing with. I'm going to go ahead and put the square root of 3 over 4 in front of the integral, and we're just trying to integrate 2 minus x squared. We're just dealing with a squared binomial here, so we can go ahead and FOIL that out, multiply it out, and then we can integrate each of these individually since they're separated by pluses or minuses. If we plug in the top bound of 2, we'll get 8/3. Luckily, when we plug in the bottom bound of 0, it produces a 0, and when we simplify that, we'll get 2 square root of 3 over 3 as the volume of this particular three-dimensional shape. Okay, here in this slide, I'm going to kind of do all the possible cross-sections or slices that could be asked that you do. And this will kind of just serve as a nice overview of the different ways, or different shapes, I should say, that you could encounter when you're looking at these problems. So I'm going to use this one area here to do all of the examples. I'm going to use the square root of x, y equals 0, and x equals 4 to define this area here that we're looking at. And in all of these slices, I'm going to be doing it perpendicular to the x-axis, which would give us a vertical representative rectangle since we're slicing perpendicular to the x-axis. So in this first one, we're going to imagine that a square is or squares, I should say, more than one, an infinite amount of them actually, are sticking out of the base of this solid. So what we need to realize is that the height of this representative rectangle corresponds to the side of one of those squares. Again, I think it's kind of helpful to imagine taking one of those squares and kind of ripping it out of the 3D solid and laying it flat over here so that we can see something. can appreciate that the height of our representative rectangle corresponds to the side length of our square. And since we're trying to find the area of that square, we need to find the height of that representative rectangle, because we know to find the area of a square, it's just the side squared. So just like we've seen many times in 7.1, to find that height, because it's a vertical height, we need to take whatever the top of the representative rectangle is touching, which is our function square root of x, and subtract away whatever the bottom of the representative rectangle is touching, which is of course 0. And the good news is, this is the only example where I'm going to put the minus 0, just for the sake of space. I'm not going to put it every single time, but just realize that of course the bottom of this representative rectangle is always touching 0, so we don't have to put that minus 0. But I'm going to go ahead and put it in this first example, just so we can make sure that we're saying it's a top minus a bottom here. Don't forget to square that, and that's it. We're done. Since we're doing everything in terms of x, of course we're going from 0 to 4 here, since we need to be looking at this from the point of view of x. So to find the volume, assuming squares are sticking out of this base, we'll integrate from 0 to 4, and the area was just the square root of x squared dx. I'm purposely not going to simplify it. Of course, that would just be x, but I'm going to just leave it like that, just so you can see how the setup went. Okay, let's look at equilateral triangles. I'm going to go ahead and erase what you saw over here, and now change this to say not the side of a square. The height of this representative rectangle corresponds to the side of an equilateral triangle, because we have those sticking out of our paper, so to speak, from this base. So that being said, if I tear out one of those representative rectangles and lay it flat over here, tear out one of these equilateral triangles and lay it flat over here, the representative rectangle, again, you can see corresponds to the length of the side of one of the equilateral triangles. So, in case, again, you didn't know this back from your geometry days, the area of a equilateral triangle, only given the side length, is square root of 3 over 4 times the side squared. And just like you saw above, to find the length of that representative rectangle, it's just going to be the square root of x minus 0. Again, I'm not going to write the minus 0 for space purposes, but that's where that's coming from. It's the top minus the bottom, so it's just the square root of x minus 0, but again, I'm neglecting to put that minus 0, and once we have that, that's it. Once you know the area of a cross-section, we want to add up an infinite amount of those areas by integrating, which of course gives us the volume. So again, we're integrating from 0 to 4. The square root of 3 over 4, I'm going to go ahead and leave in the front of the integral. And if you kind of notice something, it's really the same outcome that we got in the first example. The only thing different is we have a different constant in front of our integral. And I guess theoretically, you don't have to put it, but just to kind of see this pattern, I guess there was a 1 in front of that first example. Okay, now what if we had an isosceles right triangle with one of the legs in the base? So keep in mind, an isosceles right triangle has two legs are the same, and then it has a hypotenuse that would of course be a different length. So in this case, we're putting one of the legs that has the same length in the base of the solid. So if you imagine taking one of those isosceles right triangles and ripping it out of that 3D solid, our representative rectangle wouldn't correspond to the hypotenuse, it would correspond to one of the legs, because that's what's being stuck into the base of this yellow area that we have here. And just like in the first two examples, what we have to do is figure out, in terms of that representative rectangle, what would be the area of this isosceles right triangle. And of course, the area of a right triangle here, or it doesn't even matter that's isosceles, but in this case it is, will just of course be base times height divided by 2, or I'm going to write it as 1/2 base times height. In this case though, we know that it's an isosceles right triangle, so the base and the height are the same, so I'm going to just go ahead and say the area in terms of me calling it a leg would just be leg squared. So what we need to do is find the length of the leg. Luckily, the leg corresponds to the length of our representative rectangle, as you can see in the one that we have here on the side. And just like you saw from the first two examples, I'll put another arrow going down here, we know that the area of this isosceles right triangle is the square root of x minus 0, top minus bottom, squared, times 1/2. And again, you'll kind of hopefully appreciate here that the formula is still turning out really to be the same. The only thing that's changing now, I guess in this particular case, is we have a 1/2 in front of this integral. We can take another point of view with these isosceles right triangles, and instead of putting one of the legs in the base of this solid, we can put the hypotenuse in the base of this solid. Because of that, it's going to look a little bit different here. Our representative rectangle doesn't correspond to one of the legs, it now corresponds to the hypotenuse. So ultimately what we need to realize is we still need to know how long one of these legs is, but in terms of the hypotenuse. And just as a little review back from your geometry days, this is a 45, 45, 90 triangle. So if you know the hypotenuse, to find one of the legs, it would be the hypotenuse over the square root of 2. So I guess bottom line is, it's still this formula right here that we're using. Of course, it's 1/2 base times height, but it's really 1/2 leg squared. And since we know that the leg is h over the square root of 2, that's what we can go ahead and put there. If we simplify this a little bit, h squared, well, when we square the fraction, we'll get h squared over 2, and then the 2's in the bottom become a 1/4. How do we find h? Well, again, it's h corresponds to the length of this representative rectangle. And as you've seen in every one of these examples, the length of that representative rectangle is just found by doing top minus bottom, which you can see over here in our main picture, which is just square root of x minus 0. But again, I'm going to leave out that minus 0. And now here in this case, it turns out when you have isosceles right triangles where the hypotenuse is in the base, that's just going to produce a 1/4 in front of our integral. The last possible one that could potentially appear in an AP test question, of course there's many other shapes we could do this for, we could keep on going, but the last one we'll take a look at here is semicircles. Same idea, but keep this in mind. The diameter of the semicircle is in the base of in this solid. So that of course means the height of this representative rectangle is corresponding to the diameter of one of these semicircles. So just imagine a semicircle kind of coming out of the paper at you right here where this blue representative rectangle is. And of course there's a bunch of them, an infinite amount of them, going from left to right. So if I take one of those semicircles and take it out and rip it out and lay it flat here, the diameter of these semicircles corresponds to the length of our representative rectangle. So of course we know the area of a circle is pi r squared, but we're looking at a semicircle, so that would be half of that. And because we're dealing with diameter here and not the radius, we need to rewrite radius as diameter over 2. Once we do that, we can simplify that to be pi over 8 d squared. When you square d over 2, it's d squared over 4. 4 times 2 in the bottom would be 8. And of course we have the pi there, d squared. So bottom line is, how do we find the length of d, the diameter? Good news is, you can see in this picture, the length of that diameter corresponds to the length of our representative rectangle. To find that, it's just like the first 4 examples. We would have to take the top minus the bottom, which would be square root of x minus 0, which I'm leaving off. And once we know that area, all we need to do is integrate it, and that's the final version. We'll just have a pi over 8 in the front, as opposed to the first 4 that we did. So kind of look at this slide now, just to give a recap of it, as just the ways of looking at the different shapes. But realistically, you won't really ever have to do this again. I've kind of done the work for you, so that now all you need to realize is if you're dealing with isosceles right triangles with a leg in the base, it's just a half in front of your integral. If you're dealing with semicircles, it's pi over 8 in front of your integral. So kind of use this as a reference for the 5 different shapes you might encounter. Okay, so let's take a couple AP test free response question examples here. We're going to let R be the region in the first quadrant bounded by square root of x and x over 3. And of course, I guess this would be R. It's not labeled as R, but this would be the area R. And that's going to serve as the base of a solid. And here we're taking slices perpendicular to the y-axis. And sticking out of our paper, or this thing that we're looking at, we're going to have squares. And we want to find the volume of this solid. So first thing we have to realize is since we're slicing perpendicular to the y-axis, that's going to mean we're going to need a horizontal rectangle. As soon as you realize that, it's not necessary that you do it right away, but as soon as you realize that, we need to kind of consider that these functions need to be in terms of y instead of x. So, and that you can see right here, we're trying to find the area, but in terms of y. But luckily, we're dealing with squares, so that just means we're just dealing with side squared. So that would mean we're going to have to do a right minus a left. The length of this representative rectangle corresponds to the side length of one of our squares. So here our top function was square root of x, but of course we have to write that as y squared. And our bottom function here is going to be 3y. It used to be x over 3, but we need this in terms of y. So that's really all there is to it. Again, remember, this length right here corresponds to the side of one of our squares. And if it corresponds to the side of one of our squares, then that means we just need to find the length of that representative rectangle. And to do that, when our representative rectangle is horizontal, we'll just do right minus left, and then again, don't forget to square that entire thing. Once we realize that, we're ready to set up this problem. We know we need to integrate from 0 to 3, and keep in mind we're doing this in terms of y, so we need to be looking at this direction instead. Our functions cross at that point there, so at 3 for the y. So we're going to integrate from 0 to 3 of our area with respect to y. And after that, it's a fairly straightforward problem. We're squaring a binomial here, so we can FOIL that out. Luckily, each of those we can integrate individually, and then we can apply the fundamental theorem of calculus. When we plug in the top bound of 3, we'll get 81 over 10. Luckily, when we plug in the 0 bound, all of those become 0, so we're just left with a final volume here of 8.1. In this next example, we've actually seen in 7.1 where we found the area of R. We saw in 7.2 when we tried to find the volume of R being rotated about a certain line. And now we're seeing the third part of this problem, where now we're using R as the base of a solid, and that's the key to figuring out what kind of problem you're looking at here. It's the base of a solid, and sticking out of this base are semicircles. The next key we got to kind of realize before we continue is that we're slicing perpendicular to the x-axis. Once we kind of put these things together, we're ready to proceed. If we're slicing perpendicular to the x-axis, that means we have vertical slices, so we need to put our representative rectangle in vertically. And we can kind of maybe imagine, doesn't necessarily make this problem work any easier, but you can kind of imagine sticking out of your paper from here are semicircles. And we want to find the volume of one of those so that we can add up an infinite amount of it. So we of course know that the area of these semicircles, based on that last slide you saw, was pi over 8 d squared. So how do we find d, the diameter of one of these semicircles? Well, what we need to realize is that this height right here corresponds to d, the diameter of, let me just abbreviate it with a little picture here, it's the diameter of one of those semicircles. So to find the height of that representative rectangle, we'll just take the top minus the bottom, which would be 6. The top of this rectangle is touching 6. The bottom of the rectangle is touching 2 square root of x. Luckily, we didn't have to change that to be in terms of y, since we're doing everything in terms of x. Once you find the area of one of these semicircles, just again remember from the first slide, to find volume, all you do is integrate area. And now that we know that our area in terms of x is this function right here, we're ready to go. We can go ahead and set up this integral. And I didn't mention this at the beginning, but this is one of those problems where they want you to write, but do not evaluate the integral. So we just need to set it up. So we got to put the power of 8 in front of our integral. Careful here, we're going to go from 0 to 9 since we're doing everything in terms of x. Don't go from 0 to 6, we're going to go from 0 to 9. Our area again is 6 minus 2 squared of x, all squared. And then again, don't forget to put that final thing on there to show that we're integrating with respect to x. So don't forget the dx.